Okay, so we'll go ahead and get started. Welcome, everybody. This seemed like a fast 6 weeks to me. This summer seemed to go by so quickly, and we're excited that you all were able to participate in this project. This is our second year doing this remote, so we're getting good at something we never thought we'd have to do, but here we are. So maybe we can do just a quick round of introductions, and then we'll go ahead and get started. So I'm Mitch. I head up outreach at Caltech, and I organize this project every year with help from many people. And I'm excited to be at the end and get to see the fruits of your labors. So nice to meet you all, or e-meet you. I'll just popcorn toasted.
Okay, I'm unmuted. Hi, my name is Tostin. I'm a senior at Pasadena High School appropriately in Pasadena, California. And I was working with Bruce and John over the summer, working with Montage Mosaics. We'll get into that later, but there you go. I'm excited to present and also hear your presentations.
Thank you. Marianne?
Hi, I'm Marianne. I'm also a senior. I'm working with Javier and his two postdocs, Gulo and Riley, who's in Europe. And this summer I did research on black hole binary systems.
Looking forward to hearing about that. John?
I'm good. I'm at IPAC at Caltech. Mostly build archive information systems.
And Bruce?
Hi, I'm Bruce. I work at IPAC, where I'm a senior scientist. I've worked there for 20 years on managing archives. And I'm also the PI, the principal investigator on the Montage project that Tostin has been working on. That means I wrote the proposal and then John does the work.
Good partnership. Gulo?
Yeah, hi, I'm Gulo, and I work in the astronomy department at Caltech. I'm with Javier Garcia and Riley Connors. Yeah, we are in the NuSTAR group, which is the X-ray telescope that is run mainly by Caltech.
Thank you. And Javier will give us a silent greeting through the chat. So welcome, Javier. And we will go ahead and get started then. Did you decide who'd like to go first? We can take a volunteer.
You decide, you're the boss.
Yeah, it's easier for everybody.
Okay, Marianne, you want to kick us off?
Yes, of course. Hold on, let me screen share.
I just want, so with Javier, we agreed that we were just saying a couple of words before Marianne started. Just wanted to say that, yeah, so this was like a wonderful experience for us. Marianne is a great student, and we work in the NuSTAR group, so she had the possibility to work with like real data on like some X-ray telescopes. And what I want to say is that what Marianne has done, and like the results that she's going to present will be very useful actually for our group. So it's really an interesting project, and Marianne handled it very well. So this is just, but I leave the floor to Marianne to explain you, like to introduce you to the systems that we are working on, and yeah, and her research.
Thank you.
So hi, my name is Marianne. Today I'm going to be talking about observing black hole binaries and the research I did with that. So first thing, what's a black hole binary? Well, a black hole binary is a binary system in the sky, which is two objects orbiting each other in space. This is a picture of one. The left is the optical telescope version, and then the right is an artistic impression of one. This specific one is Cygnus X1, which is the first black hole binary. And the first time it was observed, it looked like a random blob of light moving around weirdly because, you can't really see black holes optically. So there's this mystery initially of what is Cygnus X1. And the first thing I'm going to be talking about today is how they determined it to be a black hole and how that illustrates many of the considerations taken into modern day observations of black hole binaries today. So the first hint we have is that we measured a lot of X-ray emissions from the black hole binary. And X-rays are very high energy. So the types of radiation chart, X-rays are pretty up there, which indicates that the source that the star is orbiting around is very powerful. And it also indicates a lot of mass and energy in the systems. Now, we later on found out that the X-ray actually comes from the accretion disk, which is where the black hole pulls in matter from the star, the companion star, which is the blue thing over there in the artistic impression, and compresses it with gravity. So that's where it actually comes from. The second hint we have to this binary system being a black hole is the velocity. So the companion star is moving at a very, very high velocity, which indicates that whatever it's orbiting has to have a high mass. And this is proven in, physics conceptually because with this orbital velocity equation, because if there's a high velocity, that means the net mass has to be really high. And we already know the mass of the star. So we could use that to deduce the mass of the black hole. And we deduced that the mass of the black hole, or the mass of the object that the star was orbiting, sorry, I spoiled it, but the mass of this thing the star was orbiting was too massive to be a white dwarf or a neutron star. So by process of elimination, not many things emit X-rays. By process of elimination, it had to be a black hole. So we went from this tiny optical observation where the star seemed to be orbiting nothing to this conclusion and the discovery of the first black hole binary. So now that we kind of have a grasp on the components of a black hole binary, first that it has a large mass and then also the radiation it emits, I want to delve into the X-ray part of that, the X-ray emission part of that, because that's what my research focused on. So how and why do we observe them in X-rays? So X-rays come from the accretion disk, like I said, and observing them has actually revealed that the accretion process is really dynamic because the types of X-rays emitted vary so much in energy over such short periods of time, like days even. And what do I mean by different types of X-rays? Well, the types of X-rays are distinguished by wavelength or energy. We have soft X-rays at the lower energy spectrum and hard X-rays at the higher energy spectrum. You can also distinguish them by wavelength, but for the rest of the presentation, I'm distinguishing them by energy. So what does this mean for black hole binaries when we observe them in soft or hard X-rays? Well, soft X-rays are from the optically thick disk, which is when we observe the black hole binary, the photons emitted, or the energy is dominated by the cold disk. And when we observe an overwhelmingly majority of hard X-rays, that means that most of the photons or most of the energy is coming from the hot corona. So the amount of X-rays and the type of X-rays that are coming from black hole binaries tells us which part of the black hole binary or the black hole is like dominant. So what do I mean by there's a lot of a lot of hard X-rays or a lot of soft X-rays? Well, we measure the amount of soft and hard X-rays with photon counts. So a detector telescope counts all the photons that hit it and records how much energy that photon has. For example, here there are a large number of low energy photons or soft X-ray photons. And that means that the black hole is probably dominated by soft X-ray emissions, right? Because most of the photons are coming from the soft energy band. And that indicates that, most of the energy is also dominated by the cold gas in the disk. In this graph, the photon counts versus energy is actually called the energy spectrum because it shows the distribution of photon densities over a wide spectrum of energies. So knowing the photon counts of soft X-rays and photon counts of hard X-rays allows us to determine the super important thing called the hardness ratio. And the hardness ratio basically tells us what's happening relative to the soft and hard X-rays. Because if we just know how many soft counts there are, or we just know how many hard counts there are, that's not valuable, unless we know what those counts are relative to the overall counts or relative to each other. So here, if the hardness ratio is greater than 1, that means there are more hard X-ray than soft X-rays, which means that, again, the energy is dominated by the disk. Or if the hardness ratio is less than 1, that means there are more soft X-rays, or there are more soft X-rays and wrong way around. When there are more hard X-rays, it's dominated by the corona, and if there are more soft X-rays, it's dominated by the disk. Okay. So when we compare the hardness ratios, we can compare them in this really cool diagram called the hardness intensity diagram. And the hardness intensity diagram basically plots the intensity of overall photon counts with the hardness ratio. What that does is we can find out the evolution of a black hole binary. So, for example, if we start observing the counts from here, and then all of a sudden, there are less and less hard counts and more soft counts, or at least the hardness ratio changes in that aspect. But the intensity is super high. Maybe that means like the corona is cooling down, or, the disk is heating up. So that's how conceptually it's modeled and supposed to look like. But here it's what the data sort of looks like, more or less. So I guess the model and the data. And this is actually the most accurate way of observing black hole binaries, which is through the different X-ray intensities, which is actually pretty unconventional because, for example, like stars, we usually observe with overall brightness, but overall brightness is not sufficient at describing characteristics such as what's dominating the corona or the disk, because, for example, you could have a black hole binary or a black hole with a really, really bright corona and a dim disk, or a really, really bright disk and no corona, but they would still yield the same overall brightness. So overall brightness tells us very little about what the black hole has. And so the most accurate way to observe is by measuring the types of X-rays produced, because from that we can deduce the characteristics that has produced those X-rays. And I just described the possible models, which may explain the data in my research, but a lot of it's actually model independent, meaning right now we're just studying how the data interacts with itself and how it exhibits patterns over multiple sources. So what did I research? Well, I mentioned earlier that the photons are counted with detectors or telescopes, and two that I focused on during my research were NuSTAR and RxTE. They both measure X-ray observations, but they're not exactly the same. For example, each telescope lets in a different amount of incoming light from the background of space that needs to be accounted for before recording the actual amount of light incoming from the source. And next, they also have different responses. So NuSTAR is sensitive at high energies and records more counts at high energies, versus RxTE is sensitive at low energies. And we need both of them to get a complete picture of a binary or a black hole binary. So how do we account for all these discrepancies and them just being different telescopes? Because since they have different background responses, comparing data from each telescope is like comparing apples to oranges. So my project this summer was coding a way using Python that we could compare NuSTAR and RxTE within the same framework. So the process that I used to do that was first I used the program XSpec to run simulations of fake data points for each telescope's background responses. And that's what that looks like. So the different simulations accounted for different parameters such as different fluxes and different photon indices. sorry, different simulations accounted for different permutations and various parameters. So that's why we needed to have so many. For example, I wanted to make sure I simulated what the points would look like relative to the background for a really bright source or a really dim source. And then next, I discovered a linear relationship between the hardness ratio and overall counts between NuSTAR and RxTE. And remember, hardness ratio and overall counts or intensity are the parameters we use for the HID diagram. So that's what that looks like. So hardness ratio of NuSTAR versus RxTE, overall counts of NuSTAR versus RxTE. And third, in an input and output sense, with the linear regression equations, the NuSTAR counts can be converted to RxTE counts, accounting for all the different background responses. And the best part is it's all automated because I coded it in a script using Python, which means that if you use the background response from like other telescopes, my code can still automatically discover linear relations between both photon counts. And here I just used background response as examples and how two telescopes could differ. But in reality, this code determines the linear relation regardless of how they vary. And this could also be used to find linear regression for other things other than photon counts too. You just change a few lines of code. So going forward, I want to run more simulations with more parameters, more accuracy. And I also want to be able to convert all the counts from a NuSTAR HID and hopefully make it into an RxTE version of that HID. And like, hopefully it keeps the same like graph pattern that we saw earlier, the one that like kind of looks like a turtle. So yeah, going in summary, the three questions we answered. What is a binary black hole? Well, it's something that it's two orbiting objects in space. One of them is a black hole, and we observe it with X-ray and velocity/mass. Two, how and why do we observe them in X-ray? Well, we use soft and hard X-ray to map the characteristics and which part is the dominating energy source. And then we use those characteristics and we map them to show evolution between those characteristics on an HID. And then third, what did I research? I researched converting photon counts between different telescopes to have more data points for the HID and like a more complete picture of that. Okay, and then here are my sources. Do you want me to keep screen sharing?
I think we're good. If you're finished, we'll archive this so people could refer to the references later. Thank you. Good job.
Yeah.
That was impressive. I'll start with just a simple question. Is this something you've been interested in a long time in astronomy in general, or is this something you came to fresh in this project, or?
I was pretty interested in astronomy before because I did astronomy for Science Olympiad, and then I also, dabbled a little bit in astronomy like Olympiad, like that competition. So this year for Science Olympiad, the topic was AGNs and galaxies. So I already kind of knew a little bit about accretion disks, but I was a little curious about, binary systems too. So I figured they know a lot about this.
That's terrific.
Thank you.
Any other questions?
I had one, if I may. You mentioned that you used a package called XSpec. Is this, so I'm an infrared astronomer, so I work at much lower energies. Is XSpec a community package that's widely used by X-ray astronomers?
Yeah, so you just like download it and then you can use it in your terminal and then you can access like files on your computer too. And it's very cool because you can download the version with like Python. So then you can use Python to like run scripts using the XSpec functions, such as like the functions that can make simulations and the functions that can make graphs. Pretty cool. Yeah.
I take it you found it pretty easy to learn how to use.
Yeah, I think it's because I also like came in there knowing a little bit. Well, I didn't know Python coming into this, but I knew like Java, so it was like pretty adaptable. like same like CS concepts of like just like for loops and everything. So it's like, any other questions?
Okay, fantastic. Congratulations. That's impressive.
Thank you.
And so do you feel after this summer that you have an even deeper love of astronomy?
Yeah, I think I really like astronomy, but I think I also really like coding. I think they both both the interests grew, but I think my interest for coding definitely grew a little more. I thought it was just really cool that like I just like the data manipulation aspect of it was just a lot cooler to me. So, but also astronomy because it's very cool because it has a lot of, I guess the like reason is because like again the stuff I did was pretty model independent. So a lot of the stuff that I was used to learning about astronomy with like observations and that kind of stuff and like physics and the equations didn't really apply this summer. So that's probably why.
Fantastic. Fantastic.
There's a running joke among kind of the nerdy community of science kids on the internet that astronomers just write mountains of code. So
Yeah.
definitely kind of pushed it to a certain extent.
Yeah, my code was definitely very inefficient and mostly like taken from Stack Overflow Exchange. So but it works, so that's really good. And it works pretty timely considering the amount of simulations I ran. So I was like, okay, like I guess it works. Mm-hmm.
I would say that now you are a real astronomer if your code is not efficient but it works. I think we all, it doesn't matter, like I have the feeling we all code like this because nobody did teach us how to code properly. So yeah. No, I want to say that it's like it's really remarkable what Marianne has done, and also like coming from a background she didn't know Python, she didn't know this expect software. She made it easy, but sometimes it's not extremely easy to use and to understand what it does, and in particular the wrapping that she did in Python to do her work. It was remarkable. So yeah, very good job, Marianne.
All right.
Without all of you.
Okay, we'll move over to the Berriman Good Group. Would you like to leaders kick it off before we hear from Tostin?
Yeah, if I say a couple of words. Astronomy has created a very large number of image surveys that cover a wide area of the skies in the last 20, 30 years. Individual measurements, though, are actually cover a much smaller area than astrophysical structures that you want to study. And so to really get the astrophysics out of a lot of these surveys, you actually have to create mosaics over a fairly wide area of a number of the images. And that's what montage is intended to do. It sounds easy, but it's not. For instance, backgrounds can vary, when backgrounds do vary from image to image, and you have to match them so they look right. Two overlapping images won't be quietly pointing at exactly the same region of the sky. So you have to learn how to do corrections for that. So the work we've been doing up to now has largely been about getting the processing right. But there's another aspect to this too, and that is all these image surveys are made publicly available in archives across the world. And it's sometimes not easy for astronomers to get access to these images or learn what to do to them. So Tostin has been investigating that particular aspect of the project. It's something new for us. And when I say widely available, freely available, yes, it includes students from the Pasadena Unified School District. So Tostin, take it away.
Thank you. Thank you, Bruce. So
Tostin, you're very faint.
my audio? My audio?
Yes, your audio is faint. Your screen looks good.
I can quickly switch to headphones. That may help. Sorry, a lot of luggage and stuff, but headphones are easily accessible. All right. If it's okay, I'm going to stop there for a moment. And
unknown caller.
Can't hear you.
is this any better? Or I can just talk loud too.
Yeah. Just talk loud.
It's okay. We'll make do. That don't worry.
Okay, sorry about that. But I am thankful. I just like to Mitch for connecting me to a grad student who got me a laptop, even if the audio is a little bit low. This was super helpful. Okay, so first off, I'd like to begin with saying that in the beginning of this term, I didn't really think you could do a lot of astronomy without a telescope, but this kind of completely changed my perspective on that. And it really combined, like, taught me how to apply some of the computer science knowledge that I've learned in the classroom and at my high school in the science setting, research setting. So I think Bruce had a great explanation about what montage is. It's like a toolkit for assembling mosaics of astronomical objects, right? Basically image. And Spitzer data was kind of what I focused on towards the end, because from my understanding, right, this data isn't used very often, or at least for making mosaics and so on, but it's pretty high quality and it's very dense, so it's very useful. Yeah. And a little kind of background. So one thing we do when making a mosaic is we download a lot of data, and it's often the usual products we want to use are called BCD files, right? And they're a type of FITS file, flexible image transport system. And a big part is really organizing this data. So an entire section of this presentation and this, what we call a Jupyter notebook, is dedicated to the process of collecting and organizing this data. So first off, where can we get this data? Well, PyProject, there are multiple websites, by the way, such as NAS and so on. But I went with URSA, which is the Infrared Science Archive. And I believe John had a part in setting this up, but I could be wrong. So how do we find this data? First off, we click Spitzer. Here's a lot of technical information that I don't need to go into, but we click a bunch of icons, you follow it, select your search field, and eventually you'll end up with a large table where we can draw our images from. And we can prepare, download, zip it up using unzips all the files, right? And we have roughly, if you organize it correctly, 4 folders of data, each titled with a different bandwidth. And we run a script to clean it. Now, this was a big obstacle that I encountered when making a mosaic, because even when we selected level 1, or even when I selected level 1 BCD products on our search, because you do a lot of filtering, there were still some non-BCD products in our download. So we had to run a bash, or I had to run a bash script that found these files and removed them from their directory. Roughly 4 times, since we had 4 directories. And another obstacle I encountered that I'll go into plenty of detail later, but sometimes this process can take a amount of processing power, the process of making a mosaic. So I had to reduce the number of images present within my directories or folders. I did this by removing every other, and then once I needed to get it down to a point that was more than 100, but like less than 170, I used my GUI, graphical user interface, went down a full row on the directory, and just deleted that entire column of images. So I wish my method's a little bit more scientific sometimes, but we'll see the product soon. What I had to do in making, sorry, I'm backtracking a little bit, but Montage also has like a library component that enables you to use Python with it. Normally, when I was first doing this, I used my terminal on Mac, which is kind of the like console command line interface for Linux, Mac, Unix-like operating systems. But Python helps kind of speed this up because you don't have to write a bash script that automates the process, and it lets you make like a presentational form with Jupyter Notebooks, or presentable form. So hopefully that is kind of hopefully that gets across when I show you the image at the bottom of the page. And as you can see, I've included a lot of screenshots that kind of give the idea that this lets you so I created my own, like using library, I created my own function, right, my own definition, some libraries and stuff. This is kind of technical. It's probably not worth explaining each line of my code, but this calls a definition in another file within my folder or directory that performs the sequence of steps used to make a mosaic from Spitzer data. And eventually, after these like messages here, where it basically makes a mosaic 3 times, right? And then it combines them into one color mosaic. We get this, which is an okay image or a mosaic. You have a little purple rectangular prism here that isn't ideal, and it's kind of choppy around the edges, and it's okay. I think it's very much a work in progress. And when I was making this, I ran very close to my RAM limit. So I think that if I used a machine with better specifications, or maybe twice as much RAM, I could have made something that was a little bit more polished. But I'm still very much happy with it, especially since I was within megabytes of my RAM capacity. And this is something that John made with a similar data set and the same script. And as you can see, that's what you can achieve if you have like the expertise and the ability, like the computational power to do so. So as you can see, Montage is a really powerful tool set that helps us helps me surpass, right, the kind of self-imposed barrier I had of needing a telescope, right? It's so powerful. I mean, something that Mitch mentioned in kind of beginning of our presentation session was that this is something acceptable to PUSC students, right? Or sorry, no, Bruce mentioned that. Definitely true. Like as a PUSD student and as a just student in general, right? Anybody everybody with a computer and the internet in the United States and outside of the country can make a mosaic of an astronomical object without a telescope. And that's a phenomenally powerful tool that I thought was quite interesting to use, and I really appreciate that. Thank you. Thank you.
Thank you. That was very impressive. Had you, so you already had some of the programming skills already coming to start the program, I believe. Is that correct?
Yeah. So without getting into too much detail, my high school had a 4-year series of computer science electives that I took and or am in the middle of taking. And that kind of gave me a little bit of a basic introduction to Python. But I did learn a lot, definitely, especially when it came to like montage. And I had to get like Linux distributions working when I was changing computers and so on. So there was definitely a lot of technical knowledge that I had to like soak up.
One more question. When the image is created, how do you select the colors, or is that based on their size or distance or what? I know that's a layman question, but how does the picture happen in those colors?
I was in the same position as you a couple of weeks ago. It was also something I should have explained in my main presentation. But essentially what happens is you make 3 mosaics, right? And you can assign each of these mosaics, each pertaining to a different bandwidth, right? To a different color. So with the data that I presented, we have 4 directories or folders, right? IRAC1, IRAC2, IRAC3, IRAC4. And each of these is a different wavelength. Sorry, not bandwidth. I've been saying the wrong word. Wavelength. So like 3.4 micrometers and so on. In this case, I used wavelengths 1, 2, and 4, which is apparently quite optimal for this. And I think overlapping the images is maybe like not an appropriate way to explain it, but you're essentially combining 3 mosaics, each assigned a color to produce the color image. And it ends up being quite impressive.
Thank you. So I believe Marianne has a question.
Oh yeah, I was actually just gonna ask about the same thing. So like the mosaic isn't just like a mosaic of different pictures that you're putting together. It's like a mosaic stacked wavelengths. So you can have like, but so it's like a mosaic of like stacked wavelengths, right?
Yeah, that's a way to think about it, or combined. Yeah.
Okay. Interesting. Very cool.
And Bruce and John, feel free to correct me.
You are correct. You are correct. One thing I'd add is that creating mosaics at multiple wavelengths is a very, very powerful tool in astrophysics. It's much more powerful than just working with one wavelength.
Oh yeah, so then my second question was going to be like, you mentioned that you work in infrared astronomy. So then are these wavelengths, are they like specific to infrared astronomy, or are they like across the whole radiation spectrum?
They're infrared. Spitzer was a mission run out of IPAC, and it was a dedicated infrared astronomy mission.
Oh, interesting. That was interesting because I didn't know there was like that much I guess I knew that about X-rays, but I didn't know there was that much like variation that you like enough for you to like layer on different, observations.
Yeah, I mean, you can actually, people have done this, combine X-ray observations with infrared.
Mm-hmm. Oh, yeah, that's very interesting.
Also, we plan to make this available as a service to professional astronomers. John and I will work on that. We probably changed the title from Montage Mosaics for Dummies, since that might not be taken that way.
Yeah, that was my temporary title that became permanent, and I needed to change it, but it worked for my purpose.
It's okay. I have a script. Like the script that I use is called like script 4. Like it's not even like called anything. It's called like I just like didn't change the name of it either.
Yeah. I think I need to work on my naming conventions a little bit.
There's a question from Javier in the chat. Is the software provided to the public, or is it just for IPAC use?
Yeah, it's open source. So you can get it on GitHub. Yeah.
It's freely available with an open source license. So people all over the world use it.
I think that's one of the great things about this program is you're actually contributing to the body of tools that people all over the world can use. So you're each contributing to a piece of that kind of helps everyone learn new things and make their work maybe just a little bit easier in some capacity. So that's sort of the joy of all of this. So Thorsten, you have always had an interest in computer science, I think. Are you feeling even?
The applications of computer science, definitely. I think is like a standalone abstract concept. I really needed to be like grounded in something. That's why I really liked doing this over the summer. I really got to apply it because when I was taking a computer science class, it was more like, abstraction, important concepts, but ones that didn't really mean much just in a computer science setting alone. Yeah.
I have a quick question. Well, first of all, congratulations. I think it's impressive. Like, yeah, also like your code skills are really impressive. It's probably like a silly one, but I didn't understand why your image was worse than the one that you showed afterward. I mean, it looked like pretty good for me. So maybe you can explain me what was supposed to be, or like why you said that the second one that you showed is a much better image.
Well, like a pretty big limitation was like the memory capacity of my computer, and for that reason, I dramatically cut down on the amount of data I had in each directory. So one of the bandwidths, maybe the second one, had over 1,000 files in it, which was pretty big. But then I reduced it down to roughly 150. So if you just do some like order of magnitude estimates, that's roughly a tenth, right? Like 15%. So without that data, right, there was some quality that was lost, and certain bandwidths kind of had different shapes. So like the second one kind of went in a little bit, and that's why you have that purple. I should show you visually. It's hard to describe, but when you kind of overlap them, there was that purple square that resulted from it, or rectangular prism, and that was because of kind of that mismatch.
Okay. But to me, it looked very good also, that one, but for like untrained eyes, I would say it was pretty good.
Yeah, you can very quickly get into some serious computing with this image processing.
I guess it's like a low res image versus a high res image, just because you were taking a lot of the data away just so that the program would run. But in terms of the image, it's beautiful. So yeah.
I appreciate that. Yeah.
Any other questions for either of our presenters? I think you both did an amazing job, and clearly you both brought a lot to the table when you started. And so that made the experience, I think, even richer because you were building on all these tools you already have in your tool chest. So very impressive.
Mm-hmm.
Oh, no, I don't have any more questions, but I think it was really cool, the image that you made.
Thank you.
And I just want to say, I know you're both going to be in the full college mode, college search mode in the next few months. Tostin is in the middle of a college tour right now on the East Coast. And Marianne, you're from New Jersey, right? But you're in Pasadena now, or is that right? Or
No, I'm actually from Chicago.
oh, okay.
Yeah, but yeah, I just like emailed Javier. I was like, I think your research is really cool and I would like to work with you. And he was like, I'm hosting a bunch of surfs, like, and we already have like a kind of program for like intro to research people. And I was like, oh, perfect. So yeah,
Yeah.
very well. Mhm.
Yeah, so this program obviously is for high school students, so it's like surf at the high school level. But so I hope that you both think about as you move into college that you will look at Caltech as an option for perhaps doing a surf program in the summer a couple years from now, or maybe 2 to 3, yeah. Or certainly consider Caltech as an option as you're applying for colleges. I think you both have those things that that Caltech is looking for. I think you were both in the admissions seminar last Friday, and so I hope you got some good tips and tricks from our Associate Director of Admissions, Jan. And so do think about Caltech as an option. I know, Tostin, that's your hometown, but it's still a cool place to go to school. And then certainly, no matter where you go to school, think about applying for a surf appointment for the summer in future summers, because that gives you a chance to come to campus under normal circumstances, and we will get back to normal someday. You'll have a chance to actually spend time and live on campus and have that experience, as well as doing some very cool research, which you've already started at your young ages. So congratulations.
Thank you.
Any other parting words for our students or anything else before we close out? Well, thank you all, and thanks to our mentors and hosts for making this possible, and for our students who are being brave to jump in and try new things and learn new things over the course of the summer. And congratulations all the way around. Thank you. Javier's giving us a silent celebration there. There we go. We'll say goodbye. Thank you. Take care. Bye-bye.